short question. I just expect a 45-minute answer.
So we can get back to it by the end of the presentation. Hendrik will continue the discussion as we end the seminar today. Anybody else on the phone has a quick question? Okay, no questions, so we'll just press on to the next presentation. This is kind of like a side track that I forced Richard into, which became very useful to us here, and I will piggyback on his presentation by the end. This is about using Hillary Oliver's Cylc workflow engine to optimize, objectively optimize wave physics parameters. Richard.
Okay. Okay, so yeah, what I'll run through is what do we mean by model optimization, how we might automate that, introduce Cylc for, well, hopefully I guess some of you have caught Hillary's presentation on Tuesday, did you? You gave a much more thorough demonstration of what Cylc can do, but I'll try and just summarise a few key points of it. Introduce an optimisation suite we've developed under that, and just talk through some applications to wave hindcasts, both one that I did and one that Enrique's been doing here, and a few comments about where to from there. Okay, first I'll run through what Cylc is. It's a Cylc workflow engine, developed originally by Hillary, but now getting a lot of collaboration, particularly from the UK head office. Just handles complex workflows by basically treating them as individual tasks, which can run as soon as all their preconditions and all their dependencies. So, for instance, if you're running a forecast system, there might be a set of tasks that need to be done within that. So, on the left here, that's making a forecast for one particular cycle. So, say 0 hours. This one here, this indicates, say, some data comes in or something which happens at a more or less fixed time. So that comes in, that says that when the data comes in, task A can run. There might be a weather model, B might be your wave model, C might be your storm surge model. So they need the weather model to complete, and then other tasks depend on that. There's processing tasks, and then you can have dependencies between different cycles of the model. So the weather model will need to start from a state left behind by the previous cycle. As Hillary mentioned on Tuesday, if you heard that, treating the tasks as independent so that they go whenever all their preconditions are met. It's helpful for catching up. You don't need to complete the whole forecast cycle of the whole system before the next one can go.
So is this a batch level approach, or is this internal to the code? So A, B, C, D, E are individual executables here?
Yeah, well, you can define the task whatever way you've got. You might have a script, your own scripting to run the task, whatever.
Yeah, sure, but it's an operating system level command, like running a code or something like that.
Yeah, well, it runs on a daemon, so that it just polls, it launches these tasks, just polls the state of them, it knows when they're finished, and then other tasks can interrogate that database to know the state of other tasks, which might depend.
Yeah, so what I'm going to with the question is, there's something like a Uinta system. What does this from within the executable model? That's not what you're doing here, right?
No, sorry.
Okay.
Yeah. Okay, so just to give an example, I'm going to show how we apply that for a wave hindcast. We might more originally we developed this to run our forecasting system, but since the application is going to talk about the hindcast, I'll just run through that. So in my case, I ran a hindcast based on using WaveWatch 4.18, based on air interim winds, just at the same global domain that your interim was on. Then our aerometric we used was just the normalised RMS error of significant wave height. We're comparing it with satellite altimeter data from the Information database. So to set that up in Cylc, you just have the various tasks. So for instance, we break up the hindcast into monthly chunks so that now our cycles are monthly events. Have some initial tasks before the whole system runs. You can make separate tasks and say prepare the model input file, so that needs to know what parameters you're going to be running the model with, and just panels preparing the input file. You have a separate bunch of tasks which process all your inputs with a limit and price. Task to get the restart file from the previous cycle. You're actually running the model. Define various tasks to process the outputs. Meanwhile, you have some tasks that pre-process the satellite inputs, and
Okay.
and some tasks to compute. Once that month's worth of hindcast is done, just takes the results from that, compares it to the satellite data, and produces some error statistics. So I guess some key points when we come to think of optimising this system, we're getting some final error statistics out the end. We started with a set of model parameters feeding that task. One of these tasks here is writing a number, which is the score for that. And that's after the whole set of cycles is finished. Okay, and so I just want to show you an example of error statistics, RMS error, over the globe from comparison with a satellite. And from that, we want to crunch it down into one number, which just take a spatial average. In our case, between plus or minus 61 latitude. Okay, now, when you think of, so we've got this system which starts with a set of parameters and comes out with one number at the end as a score for that model. How do we go about tuning that model? Because any numerical model is going to have a bunch of parameters which will affect the result. And each time we run the model, we've got some error metric. It might be an RMS error, which has some property that we want to get as small as possible. So we've got some set of parameters, we're getting a score out of it. So imagine a simple case where we've got two parameters. We've got the score which comes out, which might, if we actually knew the results of any possible simulation, it might look something like this. This is not a realistic case, this is just a graph. This is just a MATLAB standard plot, just to illustrate the point. So it's not a real result. So this might be how our error metric depends on the parameter choice in our national case. So as dumb modelers, we just start with some set of parameters and we'll get one value for the error metric. So we might start trying these parameters and we'll get that result. Then we sort of feel around and we'll try another one there. Oh, that's a bit better. Try another, oh, that's worse. Oh, that's better. That's worse. Oh, yeah, okay, it's sort of looking like we want to head off that way. And so basically, optimisation is a problem of exploring this parameter space to find the minimum. Now, one point I might want to make is, we're sort of, in this case, we're probably going to, hopefully we'll end up down in that minimum there. But over here, there's an even better place to find. That's a global minimum, really would like to find. So this is, there are actually lots of algorithms out there for solving this problem of optimising a function as efficiently as possible. And you can just say pick up a Python toolbox, in this case nonlinear optimisation toolbox, either in Python or C, whatever. got all sorts of different algorithms you can choose for the method it uses to explore this parameter space. I deliberately put that unreadable text so you wouldn't ask me about any of them in particular.
Explain the first one.
Because I'm not going to really go into the details of the particular algorithms we've shown. That's sort of not what this talk's about. But generally how they work is you've got to say a Python code, and it works like this. You tell it some starting value. It'll iterate through, and it'll have some subroutine with it, which the user is supposed to write, which comes back and says what your value of the objective function is, and then it'll apply some UGIB algorithm to optimise that. Well, that's all very well and good, but in our case, our objective function is the result of a fairly complex bit of code. It's running a model, it's getting data and doing all sorts of stuff with it. So it's not really inviting to write that as a subroutine for someone's optimisation code. So sort of another approach to take to that. What about instead, as our objective function subroutine, all it does is, has a lookup table which come from somewhere which has said what results we've already found. All it does, the algorithm says we want you to evaluate for some parameter set X. Well, we'll just look up our lookup table and think, oh yeah, that we've done that calculation. We can fire that back as the answer and let the optimisation code do stuff. Or it says, no, it's not in the lookup table, don't know. We'll write that out. We'll write that set of parameters out and stop. And okay, then we've got our set of parameters. That's the next set which our fancy optimisation code would have asked us to do. We'll send that off to the model system, let it evaluate it. We'll stick that back in our lookup table and then run the whole thing again. So the next time, it's got one more line in the lookup table, it'll get a bit further, and eventually it'll have enough to say, yep, that's good enough, it meets our criteria to terminate. So this idea is we don't have to code up our whole modelling system into this objective function bit of Python code. We just have a very simple generic thing, it just looks up a lookup table and either says, yes, we know the answer, or no, we don't, and stops and sends something else out. So basically, we have an optimisation program here. As far as it's concerned, the model system is just a black box which says, take some parameters, do something, and give me back a number. And it gets back that number, puts it in its lookup table, and so we've already got our model suite set up as a Cylc suite. So we've got that work's all being done. Now, as long as that can read a bunch of parameters in and write one number out to a file, you're good to go. You can top it up to our optimisation suite, which looks like this. We've put that in Cylc as well. So we've got two separate Cylc suites. We've got the pre-existing suite we set up to run our model and do all the processing, the data, etc., give a number. And we've got a fairly lightweight little optimisation suite which just runs one of these optimisation algorithms to say what's the next set of parameters we want our whole model suite to evaluate. So quite simple. So we get Cylc now, instead of cycling in time, it just cycles over iteration cycles of this optimisation process. So it's just got a bunch of tasks within that. So for each iteration, we run our algorithm to say to choose the next parameter set and evaluate. That sends off a parameter file and launches a whole new copy of our model suite, which we previously developed, to run with that set of parameter sets and give us back the answer. Okay, yeah, sorry, that starts the model. a new suite, copy of the suite, and either finishes or goes through the whole process again. Okay, so now we've applied this to, as I said, to our hindcast suite, which was running, in this case, a 1-year test period. This was run with the ST4 physics, and we picked a bunch of 19 parameters to adjust, to let this optimisation engine adjust. 8 of the wind input terms, 8 from the dissipation terms, the DIA strength, and the sea ice concentration thresholds. Ran it over a 1-year period, 1997 in that case. And this plot just shows how our error score, which was this spatially averaged RMS error, varied through the cycle. So as we change our parameters, each of these lines represent one of these 19 parameters. So we start off with this set here. In the next iteration, if you look closely, you'll see that only one of those parameters got changed. It came up with another number in here. Let the whole process go along. And eventually we come to an answer, which said that having started off with Fabrice's defaults, we got a score of 0.1436 for our spatially average RMSE, and at the end of all this we get 0.1431. Woohoo! Wasn't that a try?
But you didn't converge, did you? I mean, the top figure, top right at the end of the timeline, you're not converging.
Well, no, that just sort of says the optimisation engine says, oh, let's have one last try somewhere here and say, oh no, that didn't help it. We were really close. We were already really close to meeting our criteria. So just see after that. So yeah, we're not sort of expecting this to sort of just smoothly converge. We could be trying all sorts of things, wild guesses along the way.
Well, if you have 19 parameters, and if you would do brute force optimization over realistic ranges of it, you have to do 10 to the 20th to 10 to the 30th runs.
Sure. Yeah.
He's doing 89.
Yeah, okay, but shouldn't you come? I mean, if you like doing a gradient descent or something, you're converging at some point, don't you? Or
Yeah, but that goes back into what kind of optimization you want to do.
Yeah.
Because these things you do not want to do that.
That's really outlandish, like saying, well, we're really close now, but let's try something real, different now to see if it impacts the results in any positive ways.
Yeah. And when
let's have this.
Yeah, okay.
I want to talk way more about this, but
That's where
and
the
I guess,
genetic approach is.
I mean, you're sort of thinking of a scheme where you just purely steepest descent down to the level, but yeah, there are. This isn't. This, by the way, it isn't a global scheme. It's not trying to totally explore the parameter space. So I chose one of the more specialised local algorithms because I had a feeling that we weren't that far from best.
So without going into deep detail, all these type of optimization schemes, every single one you can interpret as some kind of targeted random search.
Mm-hmm.
And steepest descent is really good if you're already close to it. A genetic algorithm, which is a completely different approach than this, is really good if you have no idea where the optimization is in your space, and or when you have a parameter that does not behave mathematically nicely. And so you can go all kinds of different algorithms, and the fact that you get something that improves in 90 steps is pretty decent if you realize that the brute force full assessment of the system would be about 10 to the 30th tries.
So
sure.
let's
Yeah.
keep we have
Yeah.
7 minutes.
Yeah.
For
No, I mean, I should mention that there are that whole long list of algorithms in the suite, so you just click a button to try to use a different. So, yeah. Okay. So, just make one comment about why it behaved like that. Why it sort of in the early stages of the algorithm, it doesn't try every combination, but it'll just one parameter at a time, just go sort of plus delta, minus delta, and then another parameter plus minus delta. So in that early stages, it'll cycle through the parameters. So in this particular algorithm called Bobby Curé, it's forming like it's sort of forming a quadratic or n-dimensional quadratic approximation to the local region. So yeah, a pure gradient approach which so it's locally formed the sort of contour of a two-dimensional aerometric. So it is something like a steepest descent, but it does first form this quadratic approximation. So it'll have a very fixed sequence of what it'll do in the initial stages. Now, that tells us that actually we know pretty well in advance, the first whatever 2n plus 1 iterations are going to be. So we could actually be running models in parallel. So yeah, we built that into this engine. So now we don't ask we don't try and know the details of all the possible optimization algorithms. We just do a little empirical test. We'll sort of just say, well, if we tried these values, does it make any difference to what will come up next? And so empirically we can determine whether or not it's we have to wait for an answer before we launch all these parallel simulations. Okay, so that's I already showed you that, and the bias we got out of that was quite reasonable. But now I might move over to Henrique, who's taken us a bit further and done some more simulations with NCEP wins. So let you go from there.
So I'll try to fit this in the next 5 minutes. You know that I do that pretty well, right? So let's pull it over to NCEP. And first time I saw Richard's talk in Liverpool at the Wave Hindcast meeting, I thought it was really interesting because it's something that we've been trying, scratch our heads really hard to try to find out objective ways of tuning the physics parameters. I mean, we've been changing the grid resolutions, we've been changing the quality of the input fields, but we never change the physics because it's just too hard. We have too many parameters. And in this sense, Luigi Cavalieri is kind of right because he says there's just too many parameters, drives you crazy, and it might not be right. But in any case, that's what we have, and we need to tune these parameters. Because we don't have an objective way of tuning the parameters, we essentially choose one that is more relevant, which tends to be a growth rate parameter in the wind input source function, and we change that one, and we are happy with the results with our little trial and error experiments. Typically, Richard's optimization takes 89 iterations. We usually take 2 or 3 in our trial and error approaches. That's as much time as we have in an operational setting. The question is that ideal? So why worry? Yeah, we should worry. There's 19, we're changing 1. What if the other ones might have kind of a secondary impact or altogether they can change? So they are very sensitive also to the forcing fields, right? And then again, forcing fields not only wind intensity, but accuracy of location of storms, size of the storms, different storm climates and things like that. Every new atmospheric model that comes out will have a different error metric for every different type of storm population that you can imagine. How do we handle that in the wave model? We don't. So, so far we've taken the physics parameterization just by its face value. We trust the tuning that somebody else has done, like Fabrice has done really well for his European winds, right? Or we change little bit here and there the parameters that we can in the time that we have. So the absence of objective tuning framework may be really hurting us. So yeah, we should worry about that. Question is it really the best one? And there's at least one red flag. At every upgrade of GFS, we start using a different data simulation scheme. We went from a geostatistical interpolation into ENKF for all the hindcasts. Did we change the physics parameterization of the wave model? No, we didn't. So there's at least one red flag there, like the changes to the underlying atmospheric system might be so important, we're not really taking that into account. And then there's a new motivation. We're changing to FV3, and we're also changing to a coupled scenario. So things are going to become more complicated. We need something else. or do we, right? Let's just make a little test. Richard's optimization tool is very good. So what I did is I got exactly his approach, and I tried to throw it into R&D machine. Of course, it didn't work. It failed hopelessly. There were issues of Python versions. I essentially ended up having to bootstrap things around. I'm using 2 different versions of Python to run different parts of the system, but at the end of the day, I squeezed it in so much that I got it to work. I also decided to use the WaveWatch 3 version 6.03, which is kind of like the quasi-current development version. Which version are we on now? 6.03, so it is. Okay. And I use the Arduino in all operational source terms. They're the one that we are using in operations. Again, I use a global domain, 1 degree. It's kind of nice because you get all the major features, and it's fast enough that you can run this thing relatively quickly. But then I changed from the era interim wind forces that Richard used to our 2 kind of major wind field sources that we have at NCEP, the CFSR analysis and the GFS. I use the GDOT cycle because we're running hindcasts here. The Barometrics the same as Richard had, so I use the average RMS error collocated relative to infrared altimeter data between 61 and 61, 61 south, 61 north. So I did all these several adaptations, and here's what I got. Well, first of all, I wanted to actually try to show to everybody how the mind of the optimization works. And I came up with this plot here, which basically shows the different parameters that we're optimizing for the input source function, the dissipation source function at the lower left corner, one nonlinear coefficient, nonlinear interactions coefficient, weighted interactions, and then the ice concentrations as well. So I just used essentially what Richard was using and try to see what we got using our wind fields at NCEP. So what we're going to see here is just have a look at the list of parameters around the map of significant wave height RMS error. This is the first experiment with the operational settings for all the source terms. And we're starting off with an RMS error of 0.17. So on the title of the plot there, you see Cyclops optimization using CFSR winds. Experiment 1, RMS error equals 0.17 meters. The contours are coded below here at the bottom. So let's go. So I made this little animation that's showing how the optimization program is basically cycling through the different parameters as the experiment number changes. And when it's green, the title becomes green. It means that we're reducing the RMS error relative to the first experiment. And if it becomes red, we're getting it worse. And then again, flashing there, you see the different parameters that are changing. So we're starting again here. You see that it changes parameters one by one. Blue, it's changing it to a larger value than the initial one. Red, changing to a smaller value than the initial one. I kind of made the fonts proportional as well, so you can see what's going on there. So it cycles through each parameter individually, builds that lookup table, and then it starts combining things around until the 45th is when it converges. And the 45th experiment finally gives, for the CFSR winds, parameters that have changed in the following way. So you see the parameters there, that's the first experiment, RMS error of 0.17 meters. It went to RMS error of 0.13 meters. And those are the changes that operated in the different physics parameters. So the red characters, the red tags, they were reduced relative to initial one. The blue tags, they were increased. A couple were not changed. The changes weren't that large, and actually the next plot, but you can see actually here, let me go back. You can see here that the average number, the average RMS error, is not the whole story, okay? So look at the RMS error regionally, so at each different grid point. The optimization using this error metric, which is a global average, actually operated much more drastically at the grid point level. So you had reduction of RMS error in some locations of much more than just the 30% that we see on the average. Okay? So this is, to me, this is amazing, actually. Okay? And in terms of bias, so now I have the numerical values of the parameters that I used initially, and then the final values. Now just look at the bias as well, the reduction of bias. The global bias reduced a lot, but the local bias throughout the grid, it reduced dramatically. Okay? So I'm just going to flip between the first experiment with a bias of 0.2 meters to the last experiment with a global bias of minus 0.043. You can see that there are local biases. The reduction in local biases, particularly in the high latitudes, is much more dramatic. So this is something that really struck me as, wow, you know, this is something big that we have here. So in this case, the beta max reduced from 1.33 to 0.06. The other parameters reduced mildly, but essentially there was a big reduction in the swell propagation and beta max. These were the two parameters. And then again, the tau sheltering in this case changed a lot too. So you can look at it later. These presentations will be available online to see how the numbers actually behave. But I think the take-home message is dramatic changes in local value of error metrics that we're missing. Then I ran the same experiments. I used the whole year 2016 CFSR winds. I repeated the experiment using the GFS, the GDAS winds. So the surface winds that we force our operational model every day. So then again here, I'm not going to cycle through it obviously, but we started off with a lower RMS error of 0.14 because I think the parameters, they had been tuned initially to the GFS anyway. And by the 44th experiment, so it took, instead of 44 iterations to converge, I ended up with a reduction of about 20% of the global RMS error. But then again, just look how dramatically the RMS error changes locally, particularly at the high latitudes. And you will see here that these results, they are actually a consequence of small adjustments to the parameterizations. It's not like I'm going to be changing these parameters a lot. So here I'm showing the global bias again, relative to ephemeral data. So we're starting off with a bias of, it's showing the RMS error up there. The bias is actually, no, it's actually 0.12 meters. The global bias of 0.12 meters. And the last optimization cycle, we reduced the bias to minus 0.06, so there was a reduction of half of the absolute bias level. It became a little bit lower, but then again, if you look locally, the changes to bias, they're also dramatic in the high latitudes. And this resulted from a relatively minor change, mostly of beta max, the growth rate parameter, which went down from 1.33 to 1.29, 1.3. And the swell dissipation, the SWF2, you see that it went from 0.018 to 0.012. So these two changes, they basically dominated most of the impacts that we're seeing here in general bias and RMS error. So just a summary, this objective tuning can drastically improve the wave height error metrics. So basically my conclusion is that the previous configurations may not have been the best for wave models using NCEP's operational forcing model. And so the systematic calibration phase, my recommendation is that it should be added at every single upgrade that we have of of an atmospheric model that feeds the wave model. You should run this objective optimization, change the parameters accordingly, so it should be part of the downstream dependency adjustments that we do. It does provide a very handy, quick tool for us to change the wave model physics and improve the quality of our wave guidance products. And I think it will be also be very important when we move on to the NAMS coupled situation, where the complexity will be much larger and the changes are also probably going to be much greater. And here I hand it back to Richard, so he can summarize the talk.
Oh, I think we can probably just wrap up this. Yeah, mate, we've got a tool which has got a suite of a lot of algorithms you can choose if you need to do something more global, or you're happy to just really locally define what you've already got. And it can also, it's very easy to, well, I say it's very easy, I'm not arguing with you now, but if you've set up your modelling system and your data comparisons, it's pretty easy to run them through this optimization engine.
So questions?
Yeah, I have one question. It's impressive, and it's of course HS is the most important parameter, but sometimes it's very difficult to remember. Years ago, when you try to change something, when you try to get better results for HS, which is the most important, then suddenly your periods go worse. So I think it's a lot of work, but we need to include another parameters, of course. It's impressive, but I mean, what I'm afraid is that when you try to make it better HS, the period was.
Yeah,
I mean, that is something you can build into this fairly easily. That's really not a problem, because if you have spectral data, you can make that part of the score. You can do all kinds of stuff like that. But the big issue here is that you do it with a global model. And if you do it with a global model with altimeter data, although you only do the wave height, the only way you can get the swells in the Pacific right is if the spectra in the area of generation were right. And so even though you only observe a very integrated piece of the wave field, the fact that you do this full global wave model is the saving grace. And you cannot get the wave height of the tropics right from swell if you didn't get the spectral shape right when you generated it.
So the fact that you didn't deteriorate the wave heights in these regions that are dominated by swell means that you're likely not deteriorating the peak periods. But then again, this is a first approach that we're using altimeter data. Obviously, you can't have periods from the altimeter data in an objective way. And the next step of the collaboration is to expand the application of the optimization toolbox to include buoy data. And then again, we can start doing for us at NCEP Great Lakes systems, and basically look into the metrics specifically for other parameters and include that. Not only look at the results passively, but include them back in the optimization process. Right?
So, but this is 89 years of wave model simulations you did for the optimization. So, what resolution model were you running?
1 degree.
So this is a 1 degree with how many spectral components?
With 24, 25.
So it's okay. So
Just to.
yeah, sure. That's obviously because I mean, if I compare this with what you did here with what I did with the TRA optimization, so that is the really nasty piece of optimization, because you have to get this incredibly nonlinear thing that you try to optimize. So I went back from running brute force, all parameter space would have been 10 to the 30th experiments. I could do it very well in about 10 to the 6th, but that's still a lot more than you're doing here. But if you look at it, the techniques are very similar. I don't use a toolbox for it, but I wrote a script that called a bunch of scripts that I wanted to do as testing, and the same idea. You have a single script that runs everything you want, comes out with one number. And the difference I had is that I had a engine running around that could do a whole bunch of these things in parallel all the time. But that was all based on the idea that you do it with a genetic optimization. So you still do a more or less linear search, because every time you've done one experiment, you use that to define your next experiment, correct?
Well, it depends on the algorithm. which is
Okay,
in there.
sure.
So if,
Oh, you have to,
yeah,
okay.
if you've got
But that's what you did this time, correct?
well, in this algorithm, it could run in parallel because, at least in the early stages, the choices of parameters are predetermined. So yeah, it would run on those, bunch of model simulations in parallel because it could. But if your algorithm doesn't allow that, well, no, it can't.
You can use this platform to run your experiments.
Yeah.
So essentially, to build in the genetic optimization as
Yeah, sure.
as the
Yeah.
model.
Oh, yeah.
And we might
No, that was clear. That was clear to me. Yeah.
So you can kind of swap out optimization algorithms
Yeah.
at will.
Or you could change halfway through. You could start with one algorithm, and stop it, and say, "Oh, look, I'll pick up from there," and try something else.
Yeah.
Or change.
Well,
change it.
I mean, this is. You want to limit how much how much work you need to do, of course.
Yeah.
But you have to think up front of what your problem really is, and some of the issues that we don't have. Some of the issues that we knew when I was doing the MDIA is that it's incredibly nonlinear. So an incredible nonlinear problem, you do not want to do a steepest descent or anything like it, because most likely the error map looks like somebody who has the measles, okay? And there's no way a traditional steepest descent will find your way through. So you have to find something that is really good at going from a global view to finding local and being able to jump from one local minimum to another. And in that context, the genetic optimization is extremely powerful. It's not clear to me for the input and dissipation in ice how nonlinear it is. And if it's not that nonlinear, then you can use much more conventional. If it is more nonlinear, or if you want to cast a wider net, you could run a genetic optimization. You could create a population of 10, 50, 100 or so or more. And the neat thing of that is you create 100 experiments that you want to run, and if you have a big enough computer, you run them all side by side right away.
So do you think that this type of search would probably not be useful in your case for the genetic, the generalized?
From if I understand it well enough, I could have used the toolbox, but I would have used a completely different optimization strategy.
Yeah.
Because effectively, functionally, you're doing exactly what I did.
Yeah.
You're doing exactly the same thing. I just didn't need the toolbox for it. You just wrote a bunch of scripts.
Yeah.
It's interesting, just for the heck of it, to try to repeat your experiments with the genetic optimization using this toolbox and perhaps a different optimization.
I don't think you even need to do that, except for the fact that
Just to see if
I did not use as an underlying piece a single global model run. I used 13 or so different idealized cases that I all ran, and that I all compared to a full model result with the exact interactions. So my underlying way of computing the error was very, very different from here. But we've had that discussion before too. If you do a global model, then the error that you do is the error that you do against your optimization. And the key is that you do an experiment, no matter what it looks like, you come up with one number, and that number you're going to see whether to get down no matter what you do. So the strategy is the same. It would just be interesting to run what you've been doing this time, to run with the genetic optimization technique, just to see the behavior of the genetic optimization, the diversity that you get in there, if the diversity drops away or not, if you get completely different solutions than you expected in the beginning. And some of these may be completely spurious. And so you may get a really good score that has absolutely physically looks completely crap. That kind of thing.
Yeah, I was going to ask about that. Does this have anything to do with potentially overfitting solutions and things like this? Like regularization?
Well, I mean, that can be put in, that could be handled by the different algorithms in different ways, so the toolbox itself inherently doesn't.
Yeah,
work, it's
yeah,
just
yeah.
up to the
So,
algorithm.
do you think that the correlation between the parameters, because there is correlation between the parameters at the end of the day, it's like they were built in such a way that they were just not an ad hoc sequence of numbers or coefficients. So do you think that that benefits the speed in which you get to a convergent result?
Yeah, again, it's going to depend on the.
See, the problem with this, it looks good in a few steps, it does not convince me that you're anywhere near a global minimum. And so I would do at least 1 or 2 experiments where you are doing this with a hardcore genetic optimization technique. Just go bonkers, even if you have to do it with a 2-degree model instead of a 1-degree model, which gives you 10 times as much simulations at the same time. I would go with 200 or 300 or members in your population. Just run, really allow your initial setup to be a relatively broad range of reasonable values of your parameters, and see how fast this converges, and particularly look at where you converge in solution space. Do 4 or 5 of these independently with different starting conditions to see whether there are really strong attractors or not. Yeah, that will take an order or 2 of magnitude more runs. But if you do that with a slightly lower resolution model, you can address the behavior of the optimization probably better with a full genetic optimization technique.
Find some regions to then explore.
Yeah, no. What I've learned more than that, and you need to get Bob Rumban into that discussion too, because Bob knows a heck of a lot of that stuff too. But I learned an enormous amount from just as much from how it converges, and especially in the nonlinear part. You had it was very obvious that I didn't expect. It was very obvious in the genetic optimization, even early on, that there were certain configurations of quadruplets that immediately came to the front. And then how you start to mix them, that became more interesting. And if you start to mix them, then suddenly another one became more important. And so to see this search algorithm literally converge here and then look there and then look there, apart from the fact that it's really cool, it tells you a lot about the process, and the fact that starting with different initial random populations, that it very quickly goes to the same set of very limited near optimum solutions, tells you something about the fact that that quicker search algorithm probably worked well. And so if you do this once, then on the next optimization, you can take this quote-unquote shortcut because you know it's going to work.
So, just for saving time and everything, I'd like to ask if anybody on the phone would like to. Do you have any questions? Somebody on the phone? No questions. So I'd like just to remind everybody that this presentation is going to be made available online. Okay. If Richard agrees with that, yeah. So we also have a Facebook page for the Environmental Modeling Center, and it's going to be posted there as well. Richard mentioned the presentation by Hilary Oliver from NOAA about Cylc. It's a more extensive presentation with examples to this workflow manager, and it's also available online. I think that we will also make it available on Facebook or somewhere else after talking to Hilary. But ours today will definitely be there. And let's thank Richard for his visit here. And yeah, this kind of shows that we should persist with the visiting scientist program here, although it has some red tape to be gone through and things like that. These sorts of visits from collaborators that work overseas, they can really enrich our work here at NCEP. I think they have, in this case, particularly has a very concrete operational application as well. So thanks everybody. See you next time.
What do you